with Chapter 12, the normal distribution, which deals with statistics. It's a way to, and we're going to focus on basically using statistics as sort of as a consumer, because you might see this if you have children in the future and they're going to school. Sometimes in education they use it to see where you're at. They also do this a lot in medical things of, you know, like the growth of the child. Is it statistically on track? You know, some are higher, some are lower. And two of my cousins had this because they said they're just not growing very fast, and they found they did have a genetic type of dwarfism. They didn't find it till the second, or till my younger cousin. So the first cousin is kind of like he had already gone through it, so he's a little bit shorter. The other one, she got some treatments and stuff. So part of it was, you know, the statistics help in identifying when maybe there's something wrong with us, or that can be helped medically as well. So we're going to take a look at that and kind of determine, you know, percentage-wise. As I present it, we will be using the normal distribution calculator. So the slides have sort of how this has been done, all with sort of using tables and paper and pencil calculations. I'll also show you that the distribution calculator makes it much easier, but more importantly, the technology not only makes it easier, but it gives you the vision, it gives you a picture of what's going on. So it also helps you to understand more clearly as well. So we'll do that. Once we're done, the final exam instructions are here. There is a final exam review. Notice it's only going to be chapters 7 through 12. Just the midterm was 1 through 6, so we've already had that. And then the final exams here. And again, I have it set up like the last time, where you could actually go ahead. I did put links because we have a lot of these calculators, so you might want to open these up, or come back to it. When you start the let's see, I guess, oh, it's a little different. I guess I don't give you the oh yes, I do give you the password. So that password will work when you're ready. And again, I just ask that it is your own work. You don't have your uncle or something come do it for you. But and again, the reward is you get multiple chances to take it, and as you can see, up to 3 times. So take it, study it. What we're looking for is you've at least learned something enough to apply it, and if you go through the homeworks and the homework quizzes as we're doing, you should be just fine. You can use your notes, so that's the other part, is as you do the homework, take notes of what you're doing. And a lot of these, as you're going to see, is just being able to use one of these online calculators to do the mathematics, but so you understand how to kind of work through those. So that's all there. We do have class, I think it's till December 12th. So we do, you know, that's sort of the end part. Today we're finishing up the content part. So as soon as you're ready, you can take that final. Then the other thing we have is the, yes? It doesn't for the exams. That's only for the homeworks and the homework quizzes. The exam, whatever score you get, you get. But that's why I give you 3 chances. So if you get 70 on the first chance, that's a pretty good thing. Go back and it does change each question a little bit, but it means you probably will get at least that 70%. You study a little bit more, it's not too hard to get it all the way to 100%. And unlike the other exam that had 30 questions that was only supposed to have 25, this one has, 300 points. It's actually only 250 points. So you're right. You don't have to get 100%. If you get 250% out of 300, which is 75%, that's 100%. So yeah, kind of like last time, because I didn't take the extra questions out, there's sort of like some extra credit questions in there. So as long as you get to 250, you're going to get 100% of that exam score. Next semester I'll clean everything up, but so you're kind of getting a benefit of not having everything exact. Or maybe I won't. Does it kind of work kind of nice to know that you got some leeway? I think it does. So we might leave it that way. Okay. So and then the last item, or sort of the last item, is the Math of Blank project, where again, you look at something hopefully that you do. Remember, math involves something as simple as counting. Counting is math. So if you know, I had in fact a nice articles on Islamic prayers and prayer beads. You count the prayer beads. That's it. And then a lot of those. And what I found interesting, a lot of prayer beads have either 88 or 108 beads, and whether they're Buddhist or Muslim, and there's kind of that number 108 comes through. So then you start seeing patterns. In art, there's all sorts of patterns. In fact, in art, a lot of times what you see is odd numbers. In fact, I had a Hispanic artist come, and that's one of the things he noticed in his art is when he put things, they were all, there was a lot of odd numbers. I think, I'm not using this one. Let's see what happens if we unplug this one. We're still okay. Yeah. I think it was for this one, which we're not using, so that's perfectly fine. So anyway, find something that, again, the idea is if you find any topic, and hopefully something that you have like a hobby that you like doing, sports, you like listening to music, there's math in that, so it doesn't have to even be something you're producing, it could be something you enjoy doing. You enjoy watching movies, statistics about movies, right? I've got movie buffs and stuff. Whatever it is, you'll see, it doesn't have to be related to the math that we're doing in the class, but it could be. Right? So this last unit will look at statistics. Basically, you could, you like to travel. Well, I like to figure out what's the best city to go to next in the world. Statistics, right? So this kind of stuff. And again, just apply a couple concepts for math. That's your presentation. It's about a 4 to 5 minute presentation. If you do up some kind of a PowerPoint that includes some writing, that could be the written part. But the goal is that you demonstrate a way of communicating something mathematically that is in writing and oral. You can record it if you'd like. You can just come to class and talk to us about it. It's not really a form, it's not like a speech class, it's just be able to communicate. If you feel kind of shy, I've had people, can I meet you before class or after class and just talk to you? Sure, we could do that too. So again, it's just a way of testing that you can talk about something mathematical, write about it in a written form, and then we'll get you the full points. And again, that's actually, the points on that last assignment is more than each of the individual exams. So it's like a third exam, considered an oral exam, but nothing to be afraid of because you're the expert, right? You know about it. So that's all there. So what we're going to do is I'm going to use this PowerPoint for this one. Get here to chapter 12. There are recorded lectures from previous times I've done this. However, I may not have focused so much on the normal distribution calculator, although this time I will. And of course, there's all this other resources. We have the homework. We'll finish up by going through the homework quizzes, about five or six questions. And then there's some individual videos down here, which might be helpful. But let's go ahead and slideshow, here we go. Set it up to be browsed. Okay, statistics. The normal distribution. We'll skip over the objectives because we're just going to do them. So here's what a normal distribution is, and it's normal because I use it a lot. It's more just a name. It doesn't mean that this is the only way to do it. But what it is last class we talked about frequency tables and graphs, and that's bar graphs, and that's really what we've got here. Is these are bar graphs. So the height of the bar is how many items are occurring here. Let's see, do I have? Oh, I need to open up my my writing tool. This thing. We'll do that. So the height of these are going to be how often, or it could be percentage. This one is the height of men, and then the height, each bar, the height of it would be how many men are that particular height. And we kind of see this sort of overall shape of sort of what we call a bell-shaped curve, right? Goes up and comes down. And what we find is the more data we get, notice this is with a 100 men, it's kind of, you know, chunky. As we get larger and larger samples, it becomes a smoother and smoother curve. And what we see is that items where we get, this is what we call the normal distribution, that bell-shaped curve. Where it happens, where the types of things that have this sort of a shape to the data are things that are based on complex processes. Things like genetics is very complex, right? How many of you have had a genetics, or have at least like in a biology class talked something about genetics, right? How the birds and the bees talk, right? So how we come to be is a mix of all these of our parents' chromosomes, but their chromosomes are a mix of their parents' chromosomes. You know, so there's a lot of mixing going on, a lot of randomness to produce us. How many of you have a brother or sister that looks a lot like you? How many of you have a brother or sister who doesn't look anything like you? I've got both of them. One of them, I went to his wedding and they're congratulating me for getting married. I was just the best man, but I looked so much like them, even his close friends thought I was him. Okay, that's how, and he's 7 years younger than me. So I got another brother, they said, you guys don't even look related. And in fact, we have the joke, maybe one of us was taken from the wrong part of the hospital, who knows, you know? But we are very different. No, I think we're, and so that's the thing with genetics. It can sort of cause us, you know, we come from a tall family, generally we will be tall, but maybe not. So genetics causes these various physical traits that we have, and that's when we see things like a bell-shaped curve coming. So, you know, if we all were to measure our arm lengths, we would probably, again, if we had enough people here, thousands of people, we would probably see a distribution that would look somewhat normal, okay? One of the things I want to, so complex items, things that are complex, things that have a large amount of randomness to them, that's where we get these, and sort of natural things occurring. Where I'm going to kind of talk a little bit to is this concept is used in a lot of areas I don't think it should be, such as education, learning. Is learning random? I hope not. Maybe sometimes, oh, well, I'll read the book and maybe I'll learn some things, maybe I won't. Or I'll randomly read every third word and maybe I'll understand. No, usually education is directed and not random. So this idea of using a bell-shaped curve for grades, that there's only going to be so many people who can get A's, in the middle is all your C's, and then there's always going to be someone flunking. That's a concept that is not from nature, it's from biased thinking, right? We can all achieve. Now, yeah, I guarantee you I'm not going to be able to run as fast as Usain Bolt, fastest, or at least he was the fastest human. I'm not even going to be able to touch that record. But so there are some things where, you know, people are out there, but again, intelligence, that's something we can develop, and that shouldn't be, that is not random. So the other thing we find with the normal distribution is this sort of, whatever the mean is also sort of symmetric about the mean. So we talked about symmetry a little bit last time, but it's equally on both sides of whatever the average ends up being. And you could have it tightly packed or it could be loosely packed. Again, I gave the example last time of a classroom. If you're in a high school senior English class, the ages of those students are probably right around 17, 18. There might be a 16-year-old, but you're not going to get a 5-year-old in a senior, or you're not going to get an 80-year-old in a high school senior English class. You come to the community college, you might get a 12-year-old. I've had a class with a 12-year-old and an 80-year-old in the same class. So we come to community college, we have a lot more spread. But again, if we looked at all the ages, it would just be a wider spread of data, but it could very easily still be normal, this sort of shape. So what we find with a normal distribution is that, come here, is that there's this quality that when we standardize it, whatever the mean is, and we're going to talk about how this is done, but mathematically we make the mean equal to 0. And then remember, we did a calculation of standard deviation last time, which is sort of how, on average, how far away from the mean the data is. So if we standardize that what we get is from one standard deviation above the mean to one standard deviation below, it will contain 68% of the data. Okay, and that's just, it's a ballpark, it's not exact. When we use our tool to actually calculate it, you'll see it's probably like 67.98. You know, it's close, but what we do is, for ballparks, we say, okay, if one below to one above is going to be about 68%. Why? Because that's just what, again, all of this has happened from natural things. People have collected a lot of data, and this is how a normal distribution works. Okay, if it weren't 68, if it was vastly different, then it's not a normal distribution. Okay, and then what happens from 2 standard deviations below to 2 standard deviations above, that's going to contain about 95% of all the data. Okay, and again, if it doesn't, then it could be some other kind of distribution. There are things like that, but if it's a normally distributed, have the 95. And then what we see is by the time we get to 3 standard deviations below to 3 standard deviations above, that we're going to contain about 99.7% of the data. This still leaves room for having an extreme value either lower or higher. And again, if we looked at the heights of the average human, it is fairly well normally distributed because it's, you know, again, generally based on genetics. But then there are those people, sometimes it's because they have a genetic disorder that causes them to grow to 8 to 9 feet, and actually also shortens their life significantly. But there are those people, and so they're way out at that end. There's others with dwarfism or some other type of thing, that growth inhibitor, that are very short at that end. So they might not even be on this bell-shaped curve. They might be in that 0.03% that isn't contained there. So there is still room for some outliers, but again, most of our data will be within these 3 standard deviations if we have a normal distribution. Okay. And we'll work through some problems where we actually use these values, 68, 95, 99.7, and we'll see how that all works out. Okay, so here's a way, an example. Heights of males in North America. They measured a bunch of people and found a mean of 70 inches. So again, they put all that data together, added it all together, divided by however many people they had the data for. It's a couple million. They divide by a couple million, find that the average is 70. They also do the same thing. They calculate the standard deviation. So they found that the standard deviation is 4 inches. What does that mean? So the mean is 70, and then 1 standard deviation means 4 plus 70, so that would be 74. 1 standard deviation below would mean 70 minus 4, so that would give us 66. So these are kind of how we go. Find the height that is 2 standard deviations above the mean, and so notice take 2 times 4, or add 4 to it twice is the other way you could think of it. 74 plus 4 would get us to 78. So 78 is the measurement that would be 2 standard deviations above. Okay, so thinking of our last slide, 66, if I take 4 more away, that's 2 standard deviations below. So even though it's not here, what percentage of the men would be between 62 to 78 inches tall?
95%.
You got it. So that's, yeah. So this is like the -2 standard deviations. This is like the +2 standard deviations. 95% of the data is going to be between there, as long as it's normally distributed. Good. And what percent would be from 66 to 64? 74. 66 to 74. That'd be our 68. I forgot. 68 point. Yeah, just 68%. Yeah, I think it was just 68%. There we go. And if we were to go 3, you know, so but you get the idea. Okay. And so we just did this, 66 to 74, 66 to 74. We can see it's going to be 68. They walk us through the process. Take 70 minus 1 standard deviation, that's 66. 70 plus 1 standard deviation, that's 74. So that means 68%. Okay, so that's how we can kind of use this. And you're going to see the tool we have, the online calculator. Well, why not introduce it right now? I'll show you how that works. Come over here. So the online calculator, what we can do, and I just narrowed down the window, so I'm just seeing the calculator part. We can put in the mean, which they gave us, the mean was 70. We can put in the standard deviation, which they gave us was 4. And then if we want to find the percent between 2, that's what's here, we want to find the percent between 66 and 74. Watch, I'll calculate it. Notice it's not exactly 68, it's 68.27, but that's what I was saying, is that we use 68% because it's a lot easier to remember 68% than try to remember 68.27%. Okay, 68%, close enough. And again, here you see the picture that what we're finding is the percentage of measurements between 66 to 74. So that's why I like this one. It's not so abstract. You actually see what you're getting. You can also use this to get above. So if you want to find what percentage of people are taller than 74 inches, say, you could do that, and it gives you that, and you kind of see from the graph itself what you're getting. Okay, 15%, 60, almost 16. So you can use it that way. The way, what those, let's back it up here. So what we call these items is 0, -1, -2, -3. These standard deviations, we also, when we calculate them, we call those z-scores. Z comes from the German for integer. So they're the integer values, the 1, 2, 3, the -1, 2, 3. And the way we could do that is this calculation here, and we'll see this again. And again, we used to do this because we would have a table, which I'll show you, that has all the values for various z-scores, what percentage. You would look it up in a table actually, and then use that. We're going to use the online calculator, so this formula is not as important to us because the calculator has it embedded, we're going to get the answers, but this is a interim source. So what you do is you take the data item, you know, what height we want that person to be, say the mean. Again, in the case we were given that the mean was 70. So you're going to take your data value. Let's say you wanted to know what percent of people are taller than 74 inches. We'd enter 74, subtract the mean, and then divide by the standard deviation.
And you do 70 out just as like a random number, right?
Well, this 70 I'm using from the previous example that they gave us. The mean was 70. The 74 is a random thing I pulled out. Yeah. Okay. So this is my data, and I just, you know, and typically they will give you that, but this here is our mean, so that they typically will always give us, and in the bottom that's our standard deviation. And again, they give us those. We don't have to calculate them. They will tell us the mean is something, the standard deviation is something.
I know this 74 is the data, but what exactly is the mean? Or like, what's the data for? Is it like 74 people, you know, are the ones that took the test, and
well,
the mean is that they get 70% maybe?
No. This would be, if you're doing like a test, this would be someone who scored a 74% with a test that had a mean of 70.
Okay.
And a standard deviation of 4%, let's say. Then you could rate. It's a way of ranking them. What percent of the people did that? Okay.
And then the 4 would be like since you subtract 70 from 4, that's 4. That's like what you divide by?
Right. And remember, standard deviation is how spread out the data is from the mean.
Yeah. Oh, okay.
Okay. Good questions. And again, a lot of this is, it becomes more understanding the further along you go. And again, we can apply to other things like the average weight of a baby that's born. So this is saying that whatever data they had, they found that the mean weight or the average weight is 7 pounds, and a standard deviation of 0.8 pounds. So we could see if it's all normally distributed, which it might be because it's somewhat. Again, we always have to actually collect the data to see if it really is normally distributed or not. And so if you find, you know, where's my baby? It was born, oh, it's a heavy baby, you know, but it's still within 3 standard deviations. There's, you know, that happens. Is it a lighter baby? You know, so medically it might not be a, you know, there's going to be some variation. That's what happens in our world. The thing is if we're out to the extremes, that's typically medically where it might be a problem. It's either too big, too small. Yeah. So we can kind of see how that is. So that's what we use the normal distribution to kind of tell us where, you know, where does this thing rank at? Is it sort of average? Is it normal or not? And that's why I say, if we're thinking about using this to sort of rank somebody's intelligence, well, it's maybe what you know now, but there was a whole science calling the IQ, and their idea was that your intelligence quotient was something that didn't change. Now, what the knowledge you learn might be different, but that, you know, if your IQ was this number, it would be that way all the way through your life. And that's been debunked, you know. Yes, there's some people who kind of have a high level of intelligence. They might, you know, do IQ tests, they score, but IQ tests themselves are culturally biased. You can't really take out because it's, you know, it's based upon what people know. So if you don't know about this television show, that doesn't mean you're unintelligent. It just means you may be from a culture that didn't watch that show or something. So anyway, and this is sort of the calculation. This is the way they sort of do it, is they give us the mean, they give us the standard deviation, right? So those go into the formulas in those 2 places. And then they tell us what we're looking for. So they told us earlier that they want to see a baby that weighed 9 pounds, where would it rank? So we get a z-score, and what that z-score really means, it's that baby was 2.5 standard deviations above the mean. So we know it's more than 7 pounds. Since it's 0.8 to standard, 2.5, we could figure all that out, but 2 pounds above the mean, which is 2.5 standard deviations. Okay, and here we go. We're going to skip over this because, again, here's that idea coming, this IQ, Stafford Binet, and again, it's still used. I remember when I was going to grade school, we took IQ tests, and the teachers got those results. And so then they would think, oh, this is the bright child because they got the high score on this, or this one's not so, and that's, and research has shown when teachers believe that this is the bright student, they treat them like the bright student, they become the bright student. When they believe, oh, this is going to be the troublemaker because they're not very bright, they treat them that way, and so these become self-fulfilling prophecies, not because it's accurate measurements. Okay, so we'll go over this. The other thing we can do is, we talked about this with the median, is we can divide this up into what's called quartiles, or 25%. So the first 25% of the data, the next, and so we could divide it up into quartiles. Okay, and that would link up with how we might think of using the median. And with a normal distribution, the median and the mean are the same. That's why we get it symmetric. Okay. Okay. Not all systems use this one, but it's thrown out there. Sometimes we do talk about 25th percent quartile. And here's the thing, again, a little embarrassment from mine. I remember taking a test and I scored in the 10th percentile. My dad was reading it off and I said, wow, I must be pretty good, right? I'm in the top 10. That's how I read it. Wow, 10th percentile is actually, percentiles are from the bottom. That means I was in the bottom for what that was. But probably spelling. I never really worked on spelling. 10th percentile means I was in the bottom percent. So I shouldn't have been so proud and bragging about it, but hey, who cares? So again, it's a thing of, you're ranking people. Is that really the thing to do? Maybe I just need to work on my spelling. You don't have to put me in, okay, you're 10th percentile, you're always, with this idea. And I've even heard college professors at various, in the community college, will tell a student, oh, you're a 49% student, what do you expect? Well, no, you got 49% on a test, that was because maybe you didn't study or something, but don't put somebody that this is what you're always going to be doing, because you start to make people believe that, and you make it true, not because it needs to be true, but because you've crushed somebody's spirit. Okay, so again, statistics gets used in that way as well. So I'm all about ethical use of data, but not overuse, and what can help us excel rather than try to keep us in somebody else's place. So we're going to skip over this, and we'll come back. They also can use sort of this as a margin of error, so you plus or minus a percentile, but we won't get into that. We don't have to calculate those things. And just to let you know that the normal distribution isn't the only type. There's also these other kind. I believe this is, let's see, what are they? This is a skewed distribution. There's one called the Poisson, named after a guy named Poisson, that looks similar to this. Again, there's various different distributions of data, so not everything is normal. Again, normal does occur generally when we have things that are genetically based because of the randomness. Out in nature, it's a lot of times that's how things happen. But not everything is normally distributed. So now we're going to do a little bit of problem solving, and again, we're going to use our online calculator to do most of this. And I'm going to show you. So here's one. According to the Department of Health and Education, cholesterol levels are normally distributed for men between 18 to 24 years. The mean is 178.1, and the standard deviation is 40.7. So that's a cholesterol reading. So that means, plus or minus 40 is within one standard deviation, right? 178 plus 40, 178 minus 40. But then the question comes up, if say you got a test and you've got a cholesterol reading of 239, where does that place you as far as on the population scale, right? Because again, it may have a health effect. You could just see 178, that looks like maybe 1.5 standard deviations, right? Because that's about 60. Go 180 to 200, that's 20 plus another 40. So that's about 1.5, and when they do the whole calculation, that's what they get. But I'm just going to walk you through. This is the older way of doing the calculation. You get your z-score, and then what do you do with that z-score? You look it up on a table. So we came up with 1.5, and that tells us the percentile. It means that reading of cholesterol is higher than 93.32% of the population. So it means your cholesterol reading is higher than most people. And so maybe medically that might be something to be considered about, right? But that's how we would do it there. What I'm going to do is I'm going to show you, using our tool, our online tool, we can do the same thing. Let's see, let's go back. What we do is we enter the mean, 178.1. We enter the standard deviation. They gave that to us, 40.7. And then, what percentage of men in this age range have a cholesterol less than, I didn't read that, because my cholesterol's high, so I always think higher than, so less than 239. So although this tool's real nice because it makes it easy to get either less than or, so less than is below a number, so we do below, and we put in that reading, 239.15. We hit the calculate button. Oops, that's 2,000. That's 239.15. There we go. And it gives us the picture. We can see, most people are below that level. So if we were at 239, again, we're maybe on the high side. But that's exactly 93.32. What did we come up with? 93.32. Turn it into a percentage, multiply by 100, right? Come up with the same thing. Our method of using this is a little easier, right?
What would you do if you're trying to, if we're trying to go above, or like, what's like
the above?
Yeah, the above.
Then we would do the same thing. So we'd put in our number, 239.15, and we would just click on this button for above.
Okay.
And then it shows us, so we're seeing that this is the percent above, and it's only 6%, or you round it, maybe 7% of the people are above that amount. So now, I'm in a special club. I'm in with the 7%ers, but that's a high cholesterol,
yeah,
so
it's
probably not a good thing. Yeah, not where you want to be. So you take your medication, and that's what I did, and comes. It's an online calculator. It's this link right here will take you there. And I guess if you go, it's onlinestatbook.com. So anyway, I did a search. I think this is like the third one I came across, but I've used ones, I always use ones that show you the normal curve, because I want you to see the visual of what you're getting, and as well as getting it calculated. And this I like because it doesn't go through this process of having to calculate a z-score, which is kind of abstract, and then you look it up on a table and you get these values, but it's also abstract. This is much clearer because, again, what I want this class to be is about understanding what the statistics mean. Not that you can necessarily go through all these complicated, because I could get students who were actually pretty good at using all the formulas, but then they wouldn't necessarily know what they're getting. You know, they could get the answer right, and I said, well, what does that mean? Oh, I don't know. When I show you this, oh, it means that you're in the pool that's on the high end. It's pretty clear. The picture says more. Yeah. So that's all those links are in there, and then again, when you go to take the final exam, those links are embedded into the instructions for the exam. So these, you'll be able to pull all those up and use them. Well, you could, after today, yes, you could take it anytime you want. We still have 3 weeks of class remaining if you want, but you could also finish up early if you want.
Okay, so if I do finish the final exam and I have a pretty satisfactory grade, then
right,
we don't have to show up for class anymore.
No. Yeah.
Okay.
Never need to show up for class anyway, so that's why I record it. So because I know there's things that happen, as long as you engage one way or the other. It's nice having you all here, though. Don't get me wrong. So
what about you without your beautiful voice, right?
Well, thank you. So, and again, the way here we go. We use this formula to get a z-score so we can look up in the table. But if we're using our technology right, and again, in most statistics classes, what you do is you collect data, you put it all into a computer program. The computer program finds the mean, the standard deviation for you. It'll even draw up these normal curve things, if that is. But it'll also show you what your data looks like, so you know, is it even appropriate to be using a normal curve? Because maybe it's not. Maybe your data is skewed or something. Okay, so again, I show this to show you how much calculation really there is from the old methods of what you had to do. You had to calculate all these different things. What we do with now is we just take the mean, the standard deviation. So this is a different problem talking about self-employed Americans, how much they work. We can use this same tool to do any of this. We just put in the mean, in this case 44.6 hours. That's the average working for a self-employed person. Standard deviation 14.4. That tells you there's a lot of variation, 14.4 hours. So there's some people who are self-employed and working 58 hours a week. Some that are working on the other end 30 some, so it just depends. And then if we want to see, watch, United States, what percent work between 37 to 80 hours, we just put those numbers in here. We don't have to go through finding a z-score. We just realize that we want between two numbers, so we chose that one, and then we put in the numbers 37.4, 80.6, and we recalculate. We see that there's 68% of the self-employed people are working that many hours, and we can kind of see the, if it is normally distributed, we see where those people are. It's kind of towards the upper end. Hopefully the ones who are working the 80 hours are getting some good money. Hopefully they're being successful in their business. But sometimes it's the opposite. You're working 80 hours because you're not, just to try to make it, right? If you're really being successful, I'll do 30 hours and make 100,000, right? Love to do that. But sometimes we're having to work extra hours because the economy's not going well, and we're just trying to get enough to get by. But that's what this tool will do. The thing is that now we have meaningful things here. This 44.6, it's not just a zero, it's not a z-score of 0, which kind of doesn't mean anything. It's telling us we've got 44 hours as our average. And so what we've got here is meaningful stuff. Okay? And we didn't have to do all these sort of calculations. And I think we're also going to understand it. This is the Z table. So once you did your calculation, then you would look up these percentiles and you would do those things with it. Again, we don't need to use this table because we have our online calculator. Most of these places also have apps. So if you're going to do a lot of this, you download that to your phone and you have this app with you when you're doing it. And again, a lot of them are also parts of a larger statistics program. I took statistics for my graduate program. We had statistics. What they did is they taught us how to use a computer program that did all the math for us. We had to get it in there. You had to know what to ask for, but that's what I want you to understand is what really is a mean. That's the middle of the data. Standard deviation is the spread. You start to get a better feel for it when you use a tool like this one. Okay, so again, this is here, and it's in the back of a lot of statistics books. You'd look it up and you could do all the calculations, but again, it doesn't help you understand any better than what we're doing here. And this is just to show you, to get that number that we got, 68.53, right? Watch this, 68.53 or 0.6853. We got exactly the same number they came up with, but we just had to enter the facts that we were given. This thing will do it, and we got our picture. They had to do a lot of different calculations, and they still don't have an accurate picture, right? And again, here's the different ways. If you're looking for this, calculate this method. If you're looking for this type, there's 3 different ways to calculate it depending upon what you're getting. With our online calculator, one way, you just enter all the stuff in. Well, I guess there's 4 different ways, but the right here, you just check your button. Do I want above this number? Do I want below the number? Do I want between 2 numbers? Do I want outside of the 2 numbers? Right? It's just a click away. So we could see that 37.4 and 80.6. So we could see the outside, or we could see between. And again, it's just clicking back and forth, and it'll change for us. What do you see between, if you go for between and outside? What you would see is that they add to 100%. There's 100% under this curve one way or the other. And again, use the tool as we go through things. And I think this is our last slide. It is. So that means, what are we ready for now? Let's look at the homework quizzes, and I'm going to need to make this thing bigger. So actually, what I'm going to do is I'm going to bring this over here. Let's make this part bigger. So hopefully and we'll leave our calculator open because that's what we're going to probably be using for most of it. We'll look for the Chapter 12 homework quiz. Move this guy out of the way. Let's go ahead and start. Take this 10 times if needed. Let's see how many questions. Got 5 questions. So question 1, let's make this a little bit bigger. Okay, so this one actually we don't even use the calculator. Based on the graph of this normal distribution, what would the mean be?
60. Oh, sorry.
Yeah, yours might be different than mine. Yeah, so we're each different. So this is the number in the middle, right? That's going to be our mean. The median, also in the middle, same thing, 78. Okay, so that's what, let's see. What is the mode? Also in the middle, 78. Okay, so that's, and then the standard deviation. We have to do a little calculation, so it's the distance between 78 to 87, or 78 to 69, however you want to do that. That's what, 9? 78 plus 9 would get us to 87. So a little bit of calculation. Let's check our answers, and we're all good. Okay, so that's going to be your normal distribution. Oops. Oh, I don't want to leave. I want to go to the next question. Question 2, again, very similar. We were shown this. What's our mean? The one in the middle, 66. What is our standard deviation? 66 to 71 is 5. Good. And then now they're going to ask for percentage of test scores. This is where we're going to be nice to use our little online tool. So we put in the mean, 66. We put in our standard deviation, 5. And now we can answer each of these questions, a percentage. Percent of the test scores are between 61 and 71. So between, we click the between, and then we put in these scores. 61, 71, recalculate. There it is, and we see the picture. It's nice, and it looks like one standard deviation, and yeah, 68.27. Now, they're saying use the empirical rule. If I put in 68.27, I'm going to get this wrong. It's just going to be 68. So just kind of round, okay, the empirical rule is sort of rounding it. 68, 95, 99.7. Those are the three numbers for the empirical rule. Okay, so we're going to use this still to kind of verify it, but percent of the test scores is between 56 and 76. So you can see up here 56 to 76. That's 2 standard deviations below to 2 above. So if you remember from the slide, that's going to be 95%. Okay. Between 51 and 81, 51 to 81, that's 1, 2, 3 above, 3 below. Does anyone remember what that one is? 99.7. Now, I'm going to put those in there just because if you know, so they said 51 to 81. Let's calculate it. It's 99.73. Yeah, that's 99.7. Close enough. But we want to put 99.7. We don't want to put 7.3. They might mark it wrong.
Sorry, I got confused. How do you use the calculator again?
So you put in your mean and your standard deviation, and then you choose which one they're asking us. They're asking us for between, so I clicked on between, and then I put the 2 scores that they want to get between. You actually use the scores. Okay. 66 and 71. So notice that's, and again, the thing that's good with doing this is it will show us the picture. Notice that's 34%. And again, we want to use the empirical rule. That's 1 above, so that would be half of 68. So just be cognizant. We'll put in 34. We won't use the decimals because we'll round it. Percent of the scores that are less than 66. Does it make sense that that would be 50%? Since we're in the middle, 50% below, 50% above. We didn't really talk about that as an empirical rule, but that's what happens. Percent of the test scores that are less than 71, so that would be 50% plus the 34%, right? 34%. And we could also just come here, we'll click on below, we'll put in 71, and we'll see it's 84.13. Again, we just want to average it out, 84%. Using the empirical rule. And again, your numbers may be different. Probably they're similar as far as the answers probably all be the same except for the mean and standard deviation. So does that make sense, how that works? Any questions? We all good? Okay. So that was question number 2. And this is especially where it's going to be helpful because notice they don't give us any visual. Now sometimes we're going to have to do a little bit of calculation because they're actually asking us for a z-score. So we'll do that just so that we're on top of things. But when we come down here, we'll use our online calculator. The weights of a certain dog breed are approximately normal distributed with a mean of 51 and a standard deviation of 7. So in our calculator, we're going to enter those in, 51 and 7. Standard deviation of 7. I'm going to skip this first question for now. We're going to come back to it, but I just want to keep our momentum. The dog has a z-score of 121.28. What is the dog's weight? I guess we actually, they're just doing with the z-score, so let's go ahead and work this out. Okay, so we'll come back, we'll do this in order. So we're going to do this first part here. So remember the z-score comes from a formula where we have the data minus the mean, and I'm going to use this little Greek letter. This is a mu, it's a letter M in Greek, so they use that for the mean, and then for standard deviation they use this, which is a sigma. And I'm going to translate it as x minus the mean divided by the standard deviation. Okay, so you may see these symbols, that's fine. So we can calculate this is going to be, if a particular dog weighs 52 pounds, that's our data, what is the dog's z-score? Well, 52 is the data, which is the x. We subtract the mean, 51, and we divide by the standard deviation, which is 7. 52 minus 51 is 1/7. I'm not sure if it will take 1/7.
What if mine was negative?
That's okay.
Okay.
Yeah, because that means your weight was below the mean.
Yeah.
Good, good. So yeah, we might get negatives. I'm going to just try this. If I do 1/7, oh, it tells me it's not a decimal, so I gotta pull out a calculator.
0.143.
0.143. Thank you. There we go. Now it likes it. There's a 0.143. A dog has a z-score of 1.26. What is the dog's weight? Okay, so that question, we're going to kind of use the same setup. We know the score is 1.26. 1.26, not 5. And what we know is that x minus 51 divided by 7 is equal to that. If you'd like, what I'll do is I'll take this up here, because there's two types of problems. We're always given the mean and the standard deviation. Sometimes they're giving us the data and then we calculate the z-score. So that's what this one's good for. Sometimes they give us a z-score and want us to calculate the x. And so instead of doing algebra all the time, we'll do algebra one time. So the way we can do this is using algebra, we're going to solve for x. So we would multiply both sides by the standard deviation. So I'm going to do that. So you get the standard deviation times the z-score. And then since you're subtracting the mean, you add the mean. And so this is the formula you would use. Standard deviation times z plus the mean gives you your x. And so this way we don't have to do algebra every time. We can just take our standard deviation, which is 7, times the z-score, which is 1.26, and then we add the mean. So that's going to be our calculation.
I just add, what was it, 1.25 on both sides, 26 on both sides, right? Right.
Multiply 7 times both sides,
Oh,
and then add 151. Okay, 7 times 1.26 plus 51, I come up with 59.82. And you can see that if your z-score was negative, like it is in the next one, we're going to end up with a weight below the mean, right? So for this one, of negative 1.26, we take the standard deviation of 7, multiply it by negative 1.26, which will give us a negative number, and then so that'll get subtracted from the mean. And for that, I come up with 42.18. So you get a little bit of feel for how sort of this is so very abstract. The use of the z-score, again, in the older times it was necessary. They didn't have calculators, especially a couple hundred years ago. They did have those tables. Those go back to the beginning of statistics, whenever that was, and I haven't looked up the history lately. So, but they would just use these tables. This is the way when I was in school. We didn't have graphing. We didn't have these things as helpful as these, so we had to do all of this by hand, and you can look it up, and that's fine. But I think we'll get more understanding over this way. So let's check our answers. Oh, it didn't like.
It doesn't like my first one.
Yeah, it didn't like my first one either. Let's see. Why did it not like it? Okay, the breed is 52. What is the dog's z-score? 52 minus 51 is 1. 1 divided by 7.14. Oh, maybe we went to 143, which is how we rounded it. Oh, rounded to the nearest hundredth. Also, it should just be 0.14. Let's see if it'll. Yeah, so we were too accurate. And so that's probably the same thing down here. We put in 1.8, maybe we knew 52.2. No?
It was 42, wasn't it?
Oh, yeah, okay, thank you. So that was a bigger problem than that. I was off. 42. Point. Okay. We made it. That's why. I think I went through these, and I also, see, I think I give you more tries. It used to, after 2, it would time you out, so I said, let's give 3 or 4. Does all make sense? Okay. More or less. And again, this part is not something we're going to have you do all that much. But so here we're back to finding the area. So the variable is normally distributed with a mean of 18, standard deviation of 8. Again, we plug those things in. Our mean is 18. Standard deviation is 8. Use your graphing calculator to find these areas. So what is the area to the left of 19? Left, is that above or below?
Below.
Below. Good. So I marked the below. We put in 19. We calculated. The area is.
Oh, wait, so you do round though. Sorry for the last question. I'm kind of behind.
Oh, it's
the
okay.
last question. You do round though, right?
Round it to 2 decimal places.
Oh, okay.
I think
So
the nearest
it's
hundredth.
Okay, because I got 54.86, so it should be 54.86 then.
Yeah.
Okay.
That should do it.
I think I got it.
Write your answers in decimal form, round to the nearest thousandth as needed, so that's 3 decimal places. So we will do 0.549 gets rounded to 10, and when it gets rounded, it makes the 4 into a 5. Does that make sense? Okay. Area to the left of 13. So left of is also below, so we'll keep it there. All we do is change the 19 to 13, recalculate it, and we can kind of see that looks like about 13. That's a percent below, 0.266. Area to the right of 14. Right is going to be above. We put in our 14, and again, the reason I like this so much is it shows that yes, it is to the right. I've got the right answer, 0.692. Okay. And the area to the right of 22. So right is also above. We just change that to that data value, 22. We recalculate. That's going to be 0.309. So 30.9%.
So left is below?
Left is below. Yes, right is above.
Okay.
And we round that up the 8 gets rounded up to a 9. And then we have this find area between. So between is between. That's the one that's easiest. Between 13 and 25. Again, doing these by hand, that's a lot of, it's extra work. It's calculating 2 different z-scores, calculating, subtracting. But this time it shows us exactly what we have, and it gives us our answer of 0.543.
I got all of them wrong.
Well, let me see what I end up with, and I get them all right.
I don't know, I did.
Maybe, do you have different numbers?
Yeah, I've been putting in different numbers. Oh, I know why. I typed in the wrong.
Okay, there we go.
Yeah.
So, yeah, sometimes I forget to make a change, or like you see, I put in the wrong number. So that's the nice thing, is the calculator tool will always give us the right answer for the question we're asking. Just make sure we're asking the same question. So good. But again, when we do it with this process, we're typically able to find the errors as well. Okay, we got one more question. Number 5. I don't like the question, but we'll go ahead and do it. Suppose so they give us this IQ is normally distributed with a mean of 100. That's, so an average person is supposed to have a IQ of 100. I think mine is 97 or something, but my dad's was like 145, so he thought I should be a genius too, but I'm not. Okay, and then a standard deviation of 15. So we, above 15 or below 15. There we go. If you have an IQ of 95, so what is the probability that a person has an IQ greater than 95? So greater than is above, so we put in 95, and we want to see what percent of people would have a score above 95. Well, that's 63%, right? To the nearest 10th, so 63.1. So it's 0.63, multiply it by 100, you're going to get 63.1. Suppose one individual is randomly chosen, find the probability that this person has an IQ less than 125. So again, randomly chosen, less than is below. We put in 125, and we recalculate 95%. So 95% of the population, 95.2, is expected to have IQ less than that. Okay.
I'm getting weird now.
Less than is below, right?
Yes, less than is below.
This is for, because we both have the number 125, so I'm putting mine into my calculator, but it's only giving me the number 1.
Did you hit the recalculate?
Yeah, I did.
Okay. And then you have the 125 in the below?
Mm-hmm.
And for your mean and standard deviation, do you have 115?
Wait, actually, I do not. But because I missed that part. Okay, now I was confused because it didn't say anything about deviation, or I didn't see it say anything about deviation.
Okay. Yeah. So we always have to enter the mean and standard deviation, because that's what it's going to base it off of. Okay. These last ones where I have actually an additional calculation. So it says in a sample of 600 people, how many people would have an IQ less than 110? So less than is below. So for that one, we're going to put 110. This is going to give us a percentage, right? 74%, 74.75. So what we do is, since we have 600 people, we take 600 times 0.7475, which is the number we came up with, and that will tell us how many. $600 times 0.7475, 448.5. Now, you can't have half of a person, so I guess we could round it up or round it down. I don't know what this system's going to want. Sometimes they want you with a decimal. I'm just going to go 449. We'll see if it's right or not, but that's how I would do that. Sample 600 people. How many people would have an IQ greater than 140? So greater is above. So again, we just need to see the percentage. We calculate that. Very few, 0.0038. So we take our 600 times 0.0038 and 0.0038, about 2 people.
It's gonna ask you to just use the decimal.
Gonna ask what?
With the decimal. 428.
Oh, it does want the decimal
Yeah.
there. Okay, thank you. So, so it wants the decimal,
And the other one.
and the other one. So okay, I'll go back and change that one. So 448.5. This one 2.28. Let's see if that all works. Gave me credit. Good. But not too bad, right? So we can use our tool. We see the picture. Yeah. And again, when I was learning this, I'd have to use the z-scores. I'd have to draw the picture anyway by hand, and that's what took the longest time. So I'm hoping this will help you sort of speed up the process and get you more accurate and understanding what's going on from day one.